If you would have done my work for me better,
I know, right? Well,
then
yeah, this one tried that. This other girl, she says, "Oh, you know what? This is where I have my homework. I'm pretty sure you're gonna like it." I'm like,
Chapter 5.
"Your homework."
You guys got, everybody now should have their exam back. The rework, okay? You can add 5 percentage points to your score, and the way that works is it's due a week from today, right here before I start lecture. Once I start lecture, it's too late. So when you come in, put it on the desk. And what you do is you're going to turn in a week from today the original exam, right? The one that had the questions on it, on top. That goes on top. Make sure you put your name and section number on that. Then underneath that, you're going to have the work for every question that you got wrong. Okay, you know what the right answer is because it's the letters on your Scantron of the correct answer. So any one that you missed, if it's a calculation, just do the calculation correctly and show me how you can get the correct answer. If it's not a calculation, then you're going to do 2 things. You're going to explain what is wrong with the answer that you picked and why the correct answer is correct. Yes?
Would you like us to write out the problems?
No. Because you're going to turn in the original exam anyway. I'll have the problems. Just do the work, okay? And then on the very bottom, there's 3 things you turn in together. I need to know what you got wrong. So put the original Scantron, the original, not a copy, on the very bottom. Okay? And I don't have a stapler here, so staple is all together before you come to class that day. Remember, because they go everywhere if they're not stapled together. Okay? So you guys got that? Original on the top is the original exam with your name and section number written in. Then the work for every question that you got wrong. Then the original Scantron, all stapled together. This is an all or nothing deal. If you do all the questions that you got wrong correctly, you get 5 percentage points. If you do all of them except one, then you get 0 points. But you can ask me in discussions in my office hour. You can work with each other, with a tutor, it doesn't matter. So everybody should get the points if you do it. Yeah.
No matter how many you got wrong.
Right, and if you got one wrong, then you do one, you get 5 points. Right? If you got, 19 wrong, then a lot of work to do. The other thing is, okay, so all or nothing deal. I don't grade these before the final exam. If you want to keep a copy of the exam so you can study, make a copy before you turn it in. Because once you turn it in, they're not here anymore. You won't have access to them. Okay? So you guys understand that? Okay. So a week from today, next Wednesday, right here before I start lecture, original exam with your name and section number on it. Then your work on separate paper. Don't show your work on the original exam. It's too hard for me to figure out what you're doing there. And then the original Scantron underneath. And again, make sure you staple it before you come to class, right? And turn in, get 5 points.
The finals are based off the questions on these exams?
No. The final, I write the final the same way that I write these exams, but they're not the same questions. Okay? Any questions on it? So I strongly urge you to do that. A lot of times the first exam, people don't do it. And I think it is the reason they tell me is because it's not going to change their letter grade on this exam. That's totally irrelevant, right? First of all, the one thing that your grade is based on at the end of the semester is how many points you've accumulated throughout the whole semester. And so anytime you're offered the chance to get points, you should grab it and you should do it. Because you never know if that fraction of a point is going to be the difference between an 89.4 and an 89.5, because an 89.5 rounds up to a 90, which is an A, and 89.4, that's a B. Okay, so you should get every point you can. Also, the reason I offer the points is because it's good for you. You learn something, right? You work out the problems that you missed, which means you missed something about them. Something went wrong, so you should figure that out, and so you'll learn that and understand what to do in those types of problems. And you'll also figure out how I write the test, right? If you didn't already. It's pretty obvious. I tell you. I take it from the homework problems, right? So once you know how I write the exams, it should help you study better. So anyway, I urge you to do it. All right. Keep going. Chapter 5. Ionic and covalent compounds. This is one of the things we do in this chapter is nomenclature. Now, this is Chem 101, so I spent not nearly as much time on nomenclature here as I would in Chem 142 or 143, the earlier courses. So we're gonna do nomenclature. It should be a review. So I'm going to go through it real quickly. Okay. If it's not a review for you, then you should have had it before and you didn't, then you have the slides, and everything that you need should be on the slides, plus you have the textbook. If it's not a review, you're going to have to learn this stuff anyway, because nomenclature is it's the language we speak. Right, so starting out, real simple definitions here. Compound, okay, so you guys know what the elements are now. A compound, two or more elements, combined to make a compound. Two different kinds of compounds, molecular and ionic. And we're going to refine our definition. In Chem 101, we get to refine it a little farther than this. But for now, we're going to call a molecular compound anything that has all the atoms are non-metals in there. Okay? We just, and you guys remember where the non-metals are in the periodic table, right? To the right of that staircase. If there's at least one metal and at least one non-metal, then we call that an ionic compound. That's kind of a crude definition, and we'll do better later on. But for now, that's what we're going to use. So in these compounds, and this is, when we say it this way, combined in a definite proportion by mass, what we're referring to there is the law of constant composition and the law of definite proportions. These are two laws that were figured out early on in our modern understanding of chemistry by some really bright people. And what they figured was that what they figured out, and it wasn't obvious at that point, was that in any compound, the elements combine in a definite proportion by mass. And it's the same, no matter where you get that compound. Water is a real simple example. In water, it ends up that there's 2 grams of hydrogen for every 16 grams of oxygen, no matter where you get that molecule of water. So it'd be 1 to 8, 1 gram of hydrogen for 8 grams of oxygen. That's a definite proportion by mass. Combined in whole number ratios. So in water, there's 2 hydrogens for every 1 oxygen. That's H2O. That's a 2 to 1 ratio. And so there's not fractions of atoms. That's basically what they're saying. Lewis dot symbols. For an element, a Lewis dot symbol, it's a useful tool when we're explaining the chemistry that goes on, because what the symbol is, it's just a symbol for the element, like Na for sodium or K for potassium or what have you, and then the valence electrons written as dots around it. So, do you guys know what valence electrons are? Yeah. Highest N, remember that?
Right.
And also, I showed you on the periodic table, right? A handy shortcut is everything in this column is 1 valence, 2 valence electrons, 3, 4, 5, 6, 7, and 8 except helium's 2. Well, the valence electrons, I think I mentioned this, that's where the chemistry goes on. When chemistry happens, right, between 2 atoms or 2 compounds, basically they're taking their valence electrons and they're moving them around. You're making new bonds, swapping them, and something with them. And so it's useful to know how many valence electrons something has. So these are Lewis symbols. Fluorine has 7 valence electrons, so there's 7 dots like this. Oxygen has 6, right, like this. And now, for me, it doesn't matter how you arrange those dots. Like in oxygen, can you guys see this from back there? There's 2 dots on top, 2 on the bottom, 1 on each side. That's fine. It's also fine to write 2 on top, 2 on one side, 2 on the bottom, 2 on top, 2 on one side, 2 on the other, 1 on top, 1 on bottom, 2 here, 2 here. You see, it doesn't matter how you arrange it. Right? The only thing is, at least for now, you shouldn't write more than 2 dots per side. Later on, when we talk about what are called expanded octets, we're going to have to do that. But for now, just keep 2 to the side, like there's a box around it, right? 2 dots on each side. So ionic compound and bonding. When you have a crystal of salt, just table salt, sodium chloride, or any salt. Have I told you what we mean in chemistry when we say salt? I sometimes forget if I told you this or not. In chemistry, when we say salt, it's not just what you guys think probably of table salt, which is sodium chloride. It's any ionic compound. Any ionic compound is a salt, and that's what we say. So when any salt forms, it's an ionic compound, it forms what's called a lattice. So that crystal of sodium chloride it's, if you could see the atoms in there, it would look something like this idealization right there. What they do is they pack themselves, and what basically determines how they pack themselves is Coulomb's law. And, it basically says that opposite charges attract and like charges repel, right? So if two chloride ions are too close to each other, that's not going to be stable. They're going to push each other apart. It's high energy. So, or two sodium ions. So what happens is the chloride ions, they want to be as far away from the other chloride ions as they can, and yet as close to the sodium ions as they can. And the sodium ions do the opposite. They try to get as far away from the sodium ions as they can and close to the chloride ions. We'll see this in, I think, the last chapter or the next to the last chapter when we talk about crystal structures. That idea right there causes there to be some really a lot of order in the way that these ions arrange themselves. But for now, the only thing to get is that they do this kind of thing, and what holds this crystal together is Coulomb's law. The opposite charges attracting each other. This sodium ion, with its positive charge, is pulling on this chlorine ion and this chlorine ion, and they're pulling on it. Okay? And that holds it together. And this is something later, but it's a good time to talk about it now. When you toss that crystal of sodium chloride, a table salt, into water, it dissolves, right? Well, when it's dissolved, it didn't magically disappear, and it looks like it did maybe, but the sodium ions and the chloride ions are still there. The difference is that each individual ion is pulled away from the others and surrounded by water molecules. And the way that happens is a water molecule comes up here, and if it bumps up into this sodium ion, water, we're going to see pretty soon, it has a negative part and positive part to it also. Okay. Did you guys know that? Water being pulled? Yeah. So the negative part of water is going to come up close to the sodium ion. And there's going to be attraction, right? Opposite charges attract. Okay. But that one water molecule, it's not strong enough to pull that sodium ion away, because there's all these chloride ions in there pulling it back, right? But there's a lot of water, because, if you put that crystal of sodium chloride in water, there's, it's the solid. There's 10 to the 23rd of it or something like that. So they gang up, and you get a lot of water molecules, all focusing pretty much on that one sodium ion. And their combined strength ends up being enough to pull it away from the other chloride ions. And then they surround it, and they pull it away, and now it's dissolved. And it does the same thing to the chloride ions, and pretty soon all the ions are pulled away from the others, and you can't see them because you can't see an individual atom. It's too small, right? So they're all pulled away from each other. It's dissolved. They're still there. If you look at what we know about some of the things we know about ions so far. Sodium, to make the sodium ion, it's, the amount of energy required, it's basically just the first ionization energy, right? To take that first electron away. And it ends up, the number for sodium is 496 kilojoules per mole. To make the chloride ion, the amount of energy that's released is the electron affinity. And the electron affinity, again, lots of signs, for chlorine is positive 349 kilojoules per mole. And what that means is that much energy is released. So the change in energy will be negative 349. Do you guys get that? And so the overall change in energy for this process, losing an electron for sodium and adding an electron to chlorine, which is what you had to do to make salt, would be 496 minus 349, which is positive 147 kilojoules per mole. A positive energy change for a process means it's not going to happen easily. Right? You have to put energy in to do it. And that means that stuff is probably not going to be stable. Right? Because the opposite process would be a negative change in energy, which would be a good thing. But what we know about sodium chloride is, it sits in your closets for a long time, right? It's stable. We know it's stable. So there's something else going on, right? Other than just making the ions. And that's what we call, the name for that is what we call lattice energy. And what that is the amount of energy, the way that your book defines lattice energy, it's the amount of energy required to take a solid, I have a slide with the definition in a minute, a solid ionic compound, pull the ions apart from each other and make them go into the gas phase. So let me pull that up. So there, the first sentence. Energy required to convert 1 mole of ionic solid into its constituent gaseous ions, right? So we're pulling 1 mole of sodium chloride, sodium ions away from 1 mole of chloride ions, right? Makes it into the gaseous ions. And so that's going from the solid to the gaseous ions. When we make sodium chloride, you can think of the opposite as happening. You're pulling them together. So instead of having to put that much energy in, 788 kilojoules per mole, that much energy is released when you take the ions and you bring them together. So negative 788. And this comes from Coulomb's law. We're going to see lattice energy in chapter 10, I think. But we introduce it here. Your book does it here, so I talk about it. We're not going to do a lot with it yet. We're going to talk about relative lattice energies, the size of the lattice energy for different compounds, and that's about all we're doing here. Later on, we're going to do some calculations with something called the Born-Haber cycle. We'll see that in chapter 10. So what this slide does, pictures are in your textbook, it compares the magnitude of lattice energies for different ionic compounds. And because it's Coulomb's law that's determining the size of the lattice energy, there's 2 factors. The size of the charges, remember K equals Q1, Q2 over D squared? You guys remember that one? So, it's these equations right here, right? So there's 2 things that can happen. The distance between the ions can change. The farther they are from each other, the bigger D is, the smaller the force of attraction between them, right? And that means the lower the lattice energy. The closer they are together, the more strongly they're held, the bigger the force of attraction is, and the bigger the lattice energy. Okay? Then the size of the charges. The bigger the size of the charges are, one's plus and one's minus, right? So the bigger the size of the charges, the stronger they're attracted to each other, the bigger the lattice energy. The smaller the charges, the weaker they're held together, the lower the lattice energy. So if we look in the top left-hand corner, that's lithium iodide, right? So the lithium has a +1, iodide has a -1. These are the ionic radii of lithium and iodide. And the proportionality, that just means that the K, we're not worried about the K yet. You know the K in that equation? Where we're saying, okay, that's the constant proportionality, we don't care what the actual number is, right? So we get the force is proportional to -0.11. We go over here to sodium iodide. The only thing that changes, the charges are both +1 and -1, just like over there, but they're different sizes. Sodium is bigger, right? Iodide stays the same. This is still 2.20, but sodium's bigger. So this number on the bottom is bigger, so the force is a little bit smaller, which means the lattice energy is a little bit weaker. These are the lattice energies down here. 732, a little bit less, 686. You guys follow that? And then over there is potassium, so that's even bigger. So the force is smaller, and the lattice energy is smaller. Yes, Matthew?
Will we be given the lattice energy on the quiz, or will we?
Yes. Yeah. So a couple of ways. Okay. So basically, what am I going to ask you about this stuff? What's homework going to ask you to do? I'm going to compare the relative sizes of the lattice energies. So I might give you lithium iodide, sodium iodide, and potassium iodide, and ask you which one of these has the strongest lattice energy and which has the weakest, right? And what you know is that the lithium ion is smaller than sodium ion, which is smaller than potassium ion because of where they are on the periodic table. Does that make sense? And that's what we're doing up there. Down here, what we're doing is we're changing the size of the charge. And what they've done in this picture in the textbook, they've tried to keep, as best they could, the D squared pretty close, right? It changes a little bit, but this is 2.09 squared. This is 2.12 squared. This is 2.26 squared, I think. Something like that. It's pretty close, right? But what the important thing is the size of the charges. This is lithium fluoride, +1 and -1. The force of attraction is proportional to negative 0.23. Compared to magnesium iodide, it's plus 2 and negative 2, right? So it's proportional to negative 0.89. A bigger force of attraction, which means a larger lattice energy. So this number is bigger than that number, 1017, 3893. And over here, plus 3 and negative 3, negative 1.6 is what the force is proportional to. The lattice energy is 7,547 kilojoules per mole, even bigger. Okay. So that's what. So what you can do, okay? I could give you the ionic radii, and you could get this number right here, right? And then compare, lattice energies, something like that too. All right, so that's all for lattice energy analysis. Just remember that when we're talking lattice energy, we're talking Coulomb's law, and you've seen Coulomb's law a couple times now, right? So I think this is the chapter where you get to actually use it. Nomenclature. So, again, like I said, this is a brief revisit, hopefully, to nomenclature. If it's not, like I said, make sure you get this because it's real important. It's how we name stuff in chemistry, how we name compounds. And there's basically two things that we do. If we look at the formula that's written down, we need to know what the name of that stuff is so that we can talk to each other about it. And the other way around, if we see the name of a compound written, we need to know what the formula of that is so that we can do a chemistry with it. So, it started out, okay? It ends up that nowadays we have a very systematic way of naming stuff. And that's necessary. And originally there wasn't. It was just, it was either from common usage, like, water, it's been around forever, right? So, that's just what we call it in the English language or whatever language there's a name for it, right? And that's a common name. Other compounds, as they were discovered, whoever discovered them got to name them. They call it, whatever they wanted to. There's no system to it. So to know the names of the compounds, you just had to memorize them. There's no other way to do it. And there's millions of possible compounds. Right now, I think I read the other day, in the U.S., we commercially produce about 80,000 different chemical compounds, just for commercial uses. And, just knowing that, who's going to memorize 80,000 different names and get them straight, right? So we have this, you would?
Chemists.
Chemist, yeah. Just for fun, right? Anyway, so what this is some common names. The only two I expect you to memorize are the first two. Water, everybody knows H2O. I don't know if you know this one or not, but ammonia is NH3. Right, so you know that one. The others are just some examples, like stuff you might see. Baking soda, brimstone, hopefully you don't see it. Ethanol, laughing gas. Lye, caustic soda, muriatic acid, like you put in your swimming pool, right? Muriatic acid is just hydrochloric acid. Table salt, vinegar, acetic acid, wood alcohol. So, starting out with a systematic way of naming stuff. Easiest thing to name would be an element, because you have the periodic table, and the ones you have the names on, right? The name for the element's just the name, right? Nothing to that. And the symbol is just a symbol, except for the 7 diatomics. You guys know the 7 diatomics? No? So most of the elements in the periodic table, when you find them in a natural state, it's just individual atoms, some aggregation of individual atoms, right? It could be any number, right? They're just individual atoms. 7 of them, though, when you find them in their elemental form, the form that you find them naturally under these conditions, they're in pairs. They're diatomics. Okay, they always come in pairs. Hydrogen is an example. Hydrogen is a gas, and elemental hydrogen is there's 2 atoms of hydrogen. So the formula for hydrogen instead of H would just be H2. So the 7 of those, the way I remember it, there's this mnemonic Hofbrinkel, right? There, HOFBRINCL, those are the 7 diatomics. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So you definitely need to know those. There's 2 others that are not monatomic in their elemental form, sulfur and phosphorus. Sulfur is a ring of, when you find natural sulfur, it comes in rings of 8 atoms. It's a ring. And phosphorus is a square, there's 4 atoms. So elemental phosphorus is P4, elemental sulfur is S8. Your textbook is not consistent. I haven't found a textbook yet that is consistent with this. They tell you this, but then later on in homework problems, they say sulfur reacts with whatever, and they mean just S, not S8. So just so you're aware of that. Okay. So memorize the 7 diatomics. Okay, the next thing in the name are ions, starting with cations. A monatomic cation. So just monatomic means 1 atom. Cation means a positive charge. Lose 1 or more electrons. And it's just the name of the neutral element, right? And usually you say the word ion after it. So magnesium with a +2 charge, we call magnesium ion, the magnesium ion. The only thing, 2 things to watch out for, really. That is, 1, if it's a metal that can form more than 1 type of cation, so it can have a +2 or +3 charge or something like that, then in order to say the name of that cation, you have to say the name of which charge it has. And to do that, when we write it, we use a Roman numeral. So, for example, an enzyme iron is commonly found +2 or +3 charge. So if it was +2, we call it iron 2. And we write the word iron, and then in parentheses, Roman numeral 2. Okay. Iron with a +3 would be iron 3, Roman numeral 3. You don't have to memorize what charges these ions can form. You just have to know which ones can form more than 1 charge so that you know when to use the Roman numeral. Got that? Can you read that? So the question is, which ones can form more than 1 charge? Do you guys know yet? Remember from the other class? Some do, some don't. You're not going to say.
Right here.
Here's the rule that I'm going to have you guys use. Okay, it's a simplification, but it'll work for us. The first 2 columns, the alkaline metals and the alkaline earth metals, they can only form 1 charge. +1, +2, no Roman numerals for these guys. Okay? Transition elements in general can form more than 1 charge, so Roman numerals for these guys. Okay? With some exceptions. Write these down because you need to know these. Scandium forms a +3 charge only, so no Roman numeral for scandium. And you need to know that it forms a +3 charge. Zinc. I'm going to write this down in a minute. Zinc forms a +2 charge, so you need to know it forms a +2 charge. No Roman numeral for zinc. Cadmium beneath it also forms a +2 charge only. No Roman numeral. Silver, right next to that, forms a +1 charge only. No Roman numeral. Those are the only exceptions I'm going to ask you guys to remember in the transition elements.
Why is that?
It's just that those ions are particularly stable. Scandium, its electron configuration is argon 4s2 3d1. If it loses 3 electrons, it has a noble gas configuration. They don't all do that, but that's what standard does.
And then
And then the metals on the other side of the transition elements, the ones that are to the left of the staircase, except the metaloids in here. These form a +3, so no Roman numerals. Metalloid, tin and lead. These two right here, these are not transition elements, but they do form more than one charge, so they do need Roman numerals. So tin and lead are not transition metals, but they form more than one charge, so you have to use Roman numerals when you're saying the name of the cations that they do form. Tin 2, lead 4, what have you. So if it does not form more than one charge, you're not allowed to use Roman numeral. If it does form more than one charge, then you have to use Roman numeral. Mercury is a transition element. The symbol is Hg, and it can form more than one charge, so you need Roman numerals, right? And it ends up that Mercury 1, Mercury 2 are the ones they form. But Mercury 1 is, well, let's do Mercury 2 first. It's what you would expect. That's Mercury 2, okay? Mercury plus 2 charge. Mercury 1, okay? It ends up forming a diatomic cation. It's kind of like the diatomic elements. So that's Mercury 1. Whenever you say Mercury 1, it's Hg2 with a positive 2 charge. Mercury 2 is just one Hg, one Mercury with a positive 2. See the difference? Memorize that because it's just, I mean, there's reasons for that, but it ends up, the reasons you end up having to talk about relativity to answer the question, so for now we're just going to memorize it. Okay, you guys got that? Monatomic anions. So add one more electrons. The name for a monatomic anion changes a little bit from the neutral element. You take the name, these are going to be nonmetals. You're going to take the name of the element and change them into IDE. So chlorine, when it's in an anion, becomes chloride. Right? Nitrogen, when it's an anion, becomes nitride, oxide, sulfide, phosphide. Alright, you guys got that? Okay, so now we're going to start naming compounds. And the way that or the way that you should name a compound when you're looking at a formula. So what we're going to do is we're going to go through, and as we go through, I'm going to first tell you, when you look at the formula, how to say the name. And then I'm going to show you how to go backwards from the name to the formula. To name a compound when you're looking at the formula, it really helps if you can classify it. This is what you should do. You should figure out which of these 7 categories it belongs into, 6 categories. And I'll go through each of these one at a time. The reason is, you name each of these in a different way. There's different rules for naming binary molecular compounds than for naming binary ionic compounds. So let's start out with binary ionic. And so, first of all, to recognize a compound as being binary ionic, there's two parts to the name. Binary, that means there's two. Binary is two. There's two elements, two different elements in the compound, no more. Ionic, that means, at least for now, that means it's one metal and one non-metal.